Let's turn our attention to process dynamics. We're going to look at several different characteristics of processes that are very important before you will be able to control a process. First of all, you've got to know what type of process you're dealing with. There are three main types we'll talk about. You have to understand the concept of steady state gain, process gain, what these things mean, and also some of the issues that occur with processes that are very common, most having to do with delay or nonlinearities that are extremely common. The first type of process to consider is a self-regulating process. This type is easy to understand, but let's go through the diagram on the screen first of all and understand what it is. We've got a piece of pipe with flow of some type of fluid in it. It doesn't really matter what type. There's a flow valve labeled FV. Now this flow valve is a pneumatic valve. In other words, the signal that goes into it to control its positioning, in other words how far the valve is open, is a pneumatic signal. It's pressure. Usually 3 to 15 psi is standard for a industrial type of flow control valve like this. FY is a flow transducer, and what it does is it transforms the electrical signal that it's getting from the controller to a pneumatic signal that the valve can use. And so you'll notice there's a little box off to the side of the FY device labeled I/P. That stands for current to pressure transducer. So this is just a transducer that takes the electrical signal from the FIC, which is the flow indicating controller. It takes that electrical signal and then generates a pneumatic signal to actuate the valve. As I said, FIC is the flow indicating controller, and it's just a control device. This is where we'd set our proportional and integral derivative gains if we intend to use all of those. And here we could read off the current setting. In other words, where we want the flow to be and where the current flow rate is actually located, the process variable. Now, going all the way back to FT, that is the flow transducer, and it looks like that they've indicated a pressure type of device here where you've got some type of an orifice plate between the two flanges of the pipe there, and what the orifice plate does is causes a pressure drop, and that pressure drop will depend on the flow rate. The higher the flow rate, the higher the pressure drop. It's not a linear relationship, but we'll talk later about exactly how that works. It doesn't matter right now. The point is that this FT device is measuring the flow rate in some way. So it measures the flow rate, sends that signal, that information electrically to the flow indicating controller, which then selects a valve position, if you will, sends that out electronically. The I to P converter converts that to a pneumatic signal to move the diaphragm. That's what that oblong thing kind of looks like a UFO on the top of the flow valve is. It's just a diaphragm. So the pressure can move that diaphragm and thereby pull or push the stem in or out of the valve to control the flow. Now this may seem strange because it almost seems like this is not feedback control. You would think that the measurement of the flow rate would come after the flow valve, but it doesn't have to. It can come before, because if you think about it, you'll realize that if this flow valve starts to crank down on the flow upstream is going to slow down too. So it doesn't really matter exactly where the measurement is taking place, whether it's upstream or downstream. We're still measuring the flow rate, and that flow rate is certainly controlled by the flow valve. Now, turning to a self-regulating process, this is an example of one, because if you think about it, imagine that you're controlling the valve stem manually, okay, and you just pull it up a half inch or something. You'd see the flow rate change, right? The flow rate would increase because you're pulling the globe out of the seat, and so more flow can get through whatever the fluid is, but it would level off, right? It's not like it would just start increasing the flow and just increase without limit while you hold the stem in one position. It would settle to a new steady state value, right? It wouldn't really change. And you could go the opposite way. You could make a step change downward, inserting the stem into the valve and choking off flow more and thereby reducing the flow rate. Now this type of process, a self-regulating process, can use either a proportional integral or often just a simple integral controller. And if you think about it, you'll realize why this is. A proportional only controller would not work because there would have to be some error. Let's say that you change the set point. The flow rate's going at 100 GPM, you want it to go 200. And so you change the set point to 200 GPM, and what happens? Well, the controller notices there's a difference between the set point and the process variable. We want 200 GPM, we got 100. Take the difference, the error is 100 gallons per minute, no problem. It starts opening up the valve, And as the valve opens, the flow rate increases. But what will happen then is the error will go down. Let's say the flow goes to 150 gallons per minute. Now the error is only 50 GPM. With a proportional only controller, all that the error is doing is changing the valve setting from where it was originally at the original set point. So what will happen is you'll finally reach this balance between, yeah, maybe 50 gallons per minute of error is just fine because that lets me open the valve enough so that we get 150 gallons per minute of flow, and life is good as far as the proportional only controller is concerned. But of course that's not good because the process variable is not reaching the set point. We're not achieving the 200 gallons per minute that we want. So an integral controller can take care of this problem. Of course, the problem I've just described is that proportional only control has steady state offset error in presence of disturbance or a set point change. So if we use only an integral controller, then what will happen is the integral controller will integrate away from the bias position, the position where the valve was when we started the control process, when life was good and everything was working, right, until process variable is at the set point, and now we want to change either set point or there's some disturbance that causes the flow to change. The integral action will take care of that. It'll basically measure how much the set point changed, or measure the disturbance essentially, and adjust the valve accordingly so that the process variable and set point are one and the same. Now, the key feature of a self-regulating process is that it has internal negative feedback. So there's something that prevents it from going out of control. This is a process without any control that would not just run away. It's a process that has some way of not getting worse and worse as it moves away to a new set point. Integrating processes are a little bit different, and let's wrap our head around this particular process example first. This is an example where we're trying to control the level in a tank by controlling the flow rate into the tank. Now, let's assume that we've got a constant draw out. There's a constant flow out, and that doesn't change. Maybe it's 10 GPM out. Well, in order to maintain the level of the tank at one point, you're going to have 10 GPM flow in, right? 10 GPM in, 10 GPM out. Level in the tank should stay constant. But of course, if we have 11 gallons per minute flowing in, then the level of the tank is going to go up. So considering this control system, we've got a level transmitter, LT, measuring the level in the tank. Of course, that's being done by pressure as well, which makes sense. It's just sensing pressure at the bottom of the tank. And due to static pressure, that's going to change depending on the level. That signal is electronically sent to a level indicating controller, LIC, that then decides what the valve set point should be, or what the valve opening should be, I should say, and sends that signal electronically to a level transducer, LY. This is again an I to P, a current to pressure transducer, that transforms the electrical signal into a pressure signal to again drive a valve. But now, think about it, the valve is controlling the flow rate, not really the level of the tank. Obviously the flow rate into the tank affects the level of the tank. But if we somehow set the valve for 11 GPM and the outflow is 10, well, then the tank's just going to keep getting deeper and deeper, right? There's just going to be more and more liquid flowing into the tank. So what I'm trying to say is a step change in the valve, right, if we open up the valve, say a ½ inch or something, will cause an integrating and adding up change in the tank. The level in the tank will just continue to increase or decrease. If we were to clamp down the valve a little bit, let's say, and so the flow in is only 9 gallons per minute and the flow out is still 10 gallons per minute, well, eventually the tank is going to drain. With this type of system, you can simply use a proportional controller and it will work, because the natural integrating action takes care of essentially mathematically what you would need as an integral action in the controller. But if you think about the proportional action, it'll make sense, because if, let's say, the level in the tank is at 10 feet, we want it at 20 feet, okay? That's an error of 10 feet. And so what will happen is the level indicating controller will open up the valve proportional to the error, and so the valve will move away from its bias position that gave us 10 gallons per minute. It'll move away so that now there's more flow going in. Now, as the level in the tank goes on and up and gets closer and closer to that 20-foot level, what will happen is the error will be decreasing, and so the level indicating controller will be returning the valve to the bias position where we got 10 GPM before. And so a proportional only controller can work just fine. However, often you need the integral action as well in this type of process. And part of the reason for that is that many of these processes are integrating nominally, but in reality have some level of self-regulation, because with a tank like this, as the level in the tank gets deeper, the flow out is more difficult to contain constant. Unless you've got something making it constant, if you're just allowing the flow to come out based on the static pressure in the tank, well, the static pressure increases, and so the flow rate out goes up as well. So some integral action is often needed in a process like this. There are also runaway processes. The classic example is an inverted pendulum. If you've ever taken a pencil and tried to balance it on your finger, you know how difficult it is to balance something like that. Segway scooters are an example that you may be familiar with, where when you lean forward they go faster, and if it weren't for the control system, obviously, as you lean forward it would get worse and worse, right? You'd accelerate angularly faster and faster because gravity would be pulling you down harder and harder as your moment arm increases, and you'd fall flat on your face or flat on your back, one of the two. So this is a runaway type of process. With this type of process, in order to control it, it's really important to detect the rate of change of error. In other words, let's watch the process variable and see how rapidly it's changing, because when it starts to change, you don't have much time to get a hold of it and keep it from getting out of control, getting to a point where whatever you can do to control it is not enough. In our example, all we have control over is the motion of the cart back and forth. We can move it to the right or to the left to try and get that pendulum to stay upright. Now with a runaway process, if you were to make a step change in the cart, let's say you move it to the right, then obviously that makes the pendulum fall one way, and without doing any more control effort, it'll just run away. It'll fall more and more rapidly. So with this type of process, it's really important to include derivative action in the controller so that you can detect changes early on. Now, the key feature of a runaway process like this is that it has some type of internal positive feedback. So as the process variable moves away from the set point, it's driven harder and harder away from the set point. And of course, you can imagine a pendulum, the farther it is from the upright position, the more the moment due to gravity to tend to cause it to angularly accelerate and fall over. Now, there are runaway processes that would be of concern. Nuclear reactors are one that could potentially be a runaway process. One way to run a nuclear reactor is to have the fuel be above critical mass, so that the reaction is self-sustaining, and just insert control rods that moderate the neutrons that are coming out of the fuel and causing more nuclear reactions. And the farther you insert the control rods, the more the neutrons are absorbed, and so the lower the reaction rate. But the more you withdraw them, the faster and faster it goes, because what happens in a nuclear reactor is when a neutron splits one of the fuel atoms, uranium typically, what will happen is that gives off more neutrons, and so it's an exponential type of reaction or behavior, and of course can be problematic. Now, the way this is usually done to prevent these from being particularly dangerous is water is used as a moderator, and that water naturally, its properties naturally change as the temperature in the reactor change, and it tends to absorb more neutrons apparently as the water temperature goes up, and thereby is self-regulating. So instead of being a runaway process, it turns it into a self-regulating process, which is nice. Now, so fortunately, these are fairly rare, because if they were common, they'd be extremely difficult to control, or they are extremely difficult to control, or can be. And so the life of a control engineer would be a whole lot more difficult if these were just everywhere. And the key to controlling them is to add some type of negative feedback. Often natural negative feedback is added to make these self-regulating instead of positive feedback. And there was a popular series recently called Chernobyl that has a ton of inaccuracies in it. It's entertaining at best, but the facts that it portrays are pretty far off. And so I've included a video here by one of my favorite YouTubers, calls himself Thunderfoot. And he has some very good things to say and very interesting things. He's not just an armchair critique. He actually knows what he's talking about when it comes to nuclear reactions and nuclear reactors. So I've linked that here and put it on Brightspace. I'd highly recommend you watch it because it's very, very good. He explains what actually happened at Chernobyl and why it's a lack of understanding to think that a nuclear reactor could explode like an atom bomb. They can explode, don't get me wrong, obviously that has happened, but it's usually a hydrogen explosion that occurs, not a nuclear explosion. Of course, it's bad. It certainly can distribute radioactive material, which is not good, but it's still not an atom bomb. There's a world of difference between a nuclear reactor and an atomic weapon.